In the first part of this video, we will be talking about buffers. What is a buffer? A buffer is a solution that can resist pH change upon the addition of an acidic or basic component. It is able to neutralize small amounts of added acid or base, thus maintaining the pH of the solution. This is important for processes and reactions which require specific and stable pH ranges. Buffers are very much prevalent in everyday life. Human blood contains a buffer of carbonic acid and bicarbonate anions in order to maintain a blood pH between 7.35 and 7.45, as a value higher than 7.8 or lower than 6.8 can lead to death. In this buffer, hydronium and bicarbonate anions are in equilibrium with carbonic acid. Buffers are used in shampoos to balance out alkalinity that would usually burn your scalp. Citric acid and sodium hydroxide are two examples of buffers used in shampoo. Now let's go over how to find the pH of a buffer. When finding the pH of the buffer, we will be using the Henderson-Hasselbalch equation. In this equation, we will be using the pKa of the buffer as well as its acid and base. We want to remember when finding the pH of the buffer that it depends on the Ka of the acid and the ratio of acid to conjugate base. The buffer capacity is the amount of acid and base that can be absorbed before the pH changes significantly. Buffer capacity depends on the concentration of the species in the buffered solution. The more concentrated the buffer solution is, the greater the buffer capacity. How do buffers work? Let's take the buffer hydrofluoric acid and sodium fluoride as an example. When we add a base, the acid neutralizes the added base, and when we add an acid, the base neutralizes the added acid. As long as the amount of acid or base added is significantly less than the concentration of the components, the pH will change very little. Our first practice problem is what is the pH of a buffer solution that is 0.24 molar NH3 and 0.2 molar NH4Cl. The Ka for NH4 is 5.6 times 10 to the negative 10. So first we're going to write out the Henderson-Hasselbalch equation. pKa plus log of the concentration of our base over the concentration of our acid. Now we do have the concentration for our base and the concentration for our acid, but we're missing the pKa. So we're going to find the pKa from the Ka given. So the pKa is going to be equal to the negative log of our Ka, which is 5.6 times 10 to the power of negative 10. When you put that in your calculator, you're going to get 9.25. So now we can find the pH. So our pH is going to be equal to 9.25 plus the log of the concentration of our base, which is 0.24, and then concentration of our acid, which is 0.2. When you plug that in your calculator, you're going to get that the pH is equal to 9.33, which is your answer. In our second practice problem, we are preparing a buffer solution of 0.4 molar ammonia and ammonium sulfate. What is the molarity of ammonium sulfate, which is necessary to have a pH of 9, given that the pKb of ammonia is 4.74? Now, first thing we need to do is find the pKa. We know that pKa plus pKb should be equal to 14. So now we could solve for our pKa because we are given our pKb. So pKa should be equal to 14 subtracted by 4.74, which is going to be equal to, let me look at my calculator, 9.26. Now that we have solved for our pKa, we can plug in for what we do know and solve for what we don't know. So we know that we're trying to achieve a pH of 9 We have solved that our pKa was 9.26. We are given the concentration of our base, and we are solving for the concentration of our acid. So now what we could do is we just need to solve for our acid, and once we have solved for it, we should get that our concentration is 0.73 molar. The next part of this video will be on solubility, equilibrium, and KSP. Solubility in everyday life can be seen when stirring sugar in coffee and when stirring a bouillon packet into hot water, which we use when we make ramen. Ionic compounds have widely differing solubilities. Most ionic compounds that are considered to be insoluble will still dissolve to a small extent in water. That solubility can be quantified by an equilibrium constant. That equilibrium constant is known as KSP, which is equal to the mathematical product of the ion each raised to the power of the coefficient of the ion in the dissociation equation. Another key term to know for this section is a saturated solution, which is a solution which has reached equilibrium between the solid and the dissolved ions. In our first practice problem, we will be calculating the solubility of silver bromide in pure water. The KSP of silver bromide is 5 times 10 to the power of negative 13. So the first thing we want to do is write our dissociation equation. From our dissociation equation, we could then write our equation for our KSP. Because the equation is 1-to-1, our KSP equation is going to be the concentration of silver multiplied by the concentration of bromine. Now, although we're given the KSP, we are not given the concentrations of silver and bromine. So because we are in pure water and the equation is 1-to-1, both the concentrations of silver and bromine can be represented by x, which is how we're going to get x squared is equal to our KSP. And when you square root both sides, you should get that the concentration is 7.07 times 10 to the power of negative 7 moles per liter. Now we want our answer in grams per liters, and right now we have an answer in moles per liters. So we want to convert. So we're going to convert using the molar mass of silver bromide. And then from that, we should get our answer, which is 1.33 grams per liters. So the solubility of silver bromide in pure water should be 1.33 grams per liter. In our second practice problem, we will be determining whether or not a participate will form in a given reaction. As always, we are first going to write out our dissociation reaction. When determining whether or not a participate will form, we have to compare the QSP to the KSP. We are given the KSP, so we have to calculate the QSP with the initial equilibrium concentrations. So, in order to calculate the initial concentrations, the initial equilibrium concentrations, we are going to use the M1V1 M2V2 equation and use the given information to solve for the concentration. Now that we have solved for the initial equilibrium concentrations needed to solve for QSP, we can now plug them into the QSP equation and determine QSP. After we have calculated QSP, we can compare this value to the value of the KSP. In this problem, the KSP is greater than the QSP, meaning that the reaction is going to shift to the right, therefore no solid will form.